Assalamualaikum. So we are from group 16 that consists of 5 members, which is me, myself, Nur Hidayah binti Junaid, Siti Najia Auni, Adlina, Syami Binur and Yasmin, and also Muhammad Ani. So today our group is going to talk about the effect of amplification and dilution agent in transmitting Sin Nombre Virus (SNV) in the mouse population.
Assalamualaikum. I would like to introduce the topic. So, Sin Nombre Virus is a hantavirus mainly carried by the deer mice, Paromyscus maniculatus. Although SNV is not usually harmful to the deer mice itself, when humans come into contact with its bodily fluids, it can be dangerous and causes a serious disease. The paper focuses on how the SNV spreads within the deer mice population and how non-host species interacts with the deer mice and affects the SNV. So the main ecological question is related to biodiversity, which is how the increase in biodiversity affects the disease. Like it could cause dilution effect where it reduces the prevalence of SNV, or it could cause an amplification effect, which is an increase in the prevalence. So the study formulates an eco-epidemiological model to investigate the effects of the non-host species on the SNV transmission. So I would like to say why eco-epidemiological model. So it is ecological because it has carrying capacity, birth and death rate, and the competition. While epidemiological is when it divides the population into susceptible and infected. It is an SIS model. So these are the variables and parameters used. And this is the values of those parameters and variables. So how was the model formed? It's a combination of two models, which is the Lewis and the Peixoto-Abramson model. So Lewis model is a density-dependent model for the SNV persistence and separate population into susceptible and infected, while the Peixoto-Abramson model studies a single host and a single non-host using competition. So the non-host species is introduced to the model represented by Q1Z, which means the non-host population increase, it reduces the resource of the deer mouse. So a variable is added to the model, which is the interaction of non-host species and the SNV, which is gamma 1 plus delta Z, where when delta is 0, the non-host does not affect the transmission, while if delta is positive, it can increase the effective transmission rate. It is included because previous studies suggested that additional species may change the contact behavior and the stress and the immunity. So the model captures two possible effects of biodiversity, which is the amplification and the dilution effect. Now I will pass on to Jiha.
I'm Jiha. We are analyzing an eco-epidemiological model exploring the interaction between a host species divided into susceptible MS, an infection MI population, and a non-host species Z. To analyze the long-term behavior, we evaluate the system at steady state by setting all change rate to 0 by adding the equation for dms over dt and dmi over dt together. The complex disease transmission terms y1 plus sz, ms, and I completely cancel out. This leaves us an algebraic expression for total host population dynamic. Evaluating this intersection alongside the disease transmission boundary allows us to isolate and classify every possible equilibrium point in ecosystem. We will now have 4 types of steady state for this project, which is trivial equilibrium E0, boundary equilibrium that will be divided into extinction of non-host E1 and extinction of host E2, disease-free coexistence equilibria E3, and endemic equilibrium E4. First, we establish the trivial equilibrium E0 by setting all population variable into 0. This yields an equilibrium at 0, 0, 0. Epidemiologically, this represents a complete ecological collapse where both species completely vanish. This is no virus present simply because there are no remaining hosts in such state. Next, we move to boundary equilibria, which occur when one entire species faces extinction while the other survives. Under the first subcase E1, the non-host species is entirely absent at z equals to 0. Next, by solving the remaining host equation reveals that the susceptible population reach a steady state balance purely by birth, natural death, and carrying capacity, while the infection is eliminated. Under the second subcase E2, the host species goes entirely extinct. Perhaps due to the high disease mortality, this allows the non-host species to stabilize independently and its carrying capacity K2 entirely clearing the host species virus from the ecosystem. The third scenario is the disease-free coexistent equilibrium E3, where the susceptible host successfully coexists alongside the non-host species but the virus is driven to extinction. To solve this mathematically, we substitute the non-host equilibrium equation Z star equals to K2 minus Q2 MS star directly into our primary host equation. Isolating MS star yields a comprehensive expression structured by competitive and density dependent factors. This is one of the most critical states by studying ecological prevention. Both species successfully coexist in an environment, but the virus is completely eliminated. This state is ideal for examining whether the presence of the non-host Z acts as a dilution agent that can naturally keep the host population healthy and prevent outbreaks without necessitating species eradication. Finally, we evaluate the endemic equilibrium E4, which represented a fully chronic coexisting ecosystem. Here, susceptible host, infected host, and non-host all persist together at non-zero values. By setting our infection transmission change to 0 and factor out in infected population MI, we solve for the exact equilibrium of the susceptible population MS star in terms of recovery, death, and transmission rate. Substituting MS star and Z star back into our primary host equation allow us to isolate the chronic infection level MI star. Epidemiologically, this state represents ultimate permanence. While the disease establishes itself permanently within the host population, the entire system reaches a stable compromise. No single component, the pathogen, the pathogen, the host, or the companion species, drive any of the other extinction.
Thank you, Najiha. My name is Aumi Atlina binti Manu Azam, and I will be presenting the Jacobi matrix and local stability analysis for our eco-epidemiological model of Sin Nombre Virus transmission. We will look at how we realize our non-linear differential system, compute the partial derivative, evaluate the eigenvalues at key equilibrium points, and analyze how change parameters affect disease persistence. After we compute each of the partial derivative and substitute our total host identity n equal to ms plus mi into our equations and taking all first order partial derivative, we arrive at this comprehensive 3x3 Jacobi matrix J shown on the slide. By evaluating this matrix at each of our calculated equilibrium points, we can derive the eigenvalues that determine if a steady state is locally stable or unstable. And this is the list of parameters that we use to calculate the steady state. Let us begin our analysis with the simplest boundary case, the trivial equilibrium E0, located at 0, 0, 0. This represents a scenario of total ecological collapse where all species, susceptible mice, effect mice, and non-hosts are entirely absent. When we substitute zeros into our main Jacobian formula, and this is the eigenvalues that we get, after plugging in our standard parameters value, this is the value that we get for lambda 1, lambda 2, and lambda 3. Because we have a combination of two positive eigenvalues and one negative eigenvalue, the trivial equilibrium is locally unstable and behave as a saddle point. From a biological perspective, this instability is great news for the ecosystem. It indicates that if a small group of mice or non-hosts enters this desolate area, they won't face total extinctions. Rather, they will take advantage of the plentiful resource, reproduce, and grow. Next, we evaluate steady states at boundary equilibrium E1, which represent non-host extinctions. In this state, the non-host species is gone, the virus is completely clear, and our susceptible host population rests exactly at its carrying capacity equilibrium, giving us a simplified steady state coordinate of m star s equal to 20.0002. Evaluate our Jacobian at m star s 00, give us the structural matrix on the slide, yielding 3 distinct eigenvalues. Because we have one negative real eigenvalue alongside two positive ones, this boundary state is also locally unstable saddle point. This indicates that an ecosystem made up solely of healthy deer mice cannot sustain its purity indefinitely. Our second boundary equilibrium is E2, the non-host only state located at 00 Z star, where the non-host expand to its independent carrying capacity K2 equal to 50, while the deer mouse host population has completely gone extinct. We compute our Jacobian matrix and plug in our standard parameters value. This is the value that we get for lambda 1, lambda 2, and lambda 3. Here we have two negative eigenvalues, but we are still left with one positive eigenvalues. Therefore, E2 is yet another unstable saddle point. This brings us to one of the most critical states for studying ecological prevention, the disease-free coexistent equilibrium, or DFE, denoted as E3. Here, both the host and non-host live together successfully, but the pathogen is entirely absent. When we evaluate the Jacobian at E3, we can isolate a highly specific eigenvalue from the center diagonal entry, the disease invasion eigenvalue, which is lambda 2. As shown by the formula on the slide, lambda explains how the ecosystem responds when a small viral load is introduced into a clean, coexistent community. If lambda 2 is negative, the ecosystem will naturally stamp out the disease. If it is positive, the disease will successfully invade. To determine the other two eigenvalues that influence the basic ecological stability between the susceptible mice and the non-host agent, we focus on the 2x2 ecological submatrix J echo formed by rows and columns 1 and 3. We can solve for lambda 1 and lambda 3 analytically using the characteristic trace and determinant formula displayed on the slide. The trace captures the combined density-dependent decay of both populations, while our determinant integrates the interspecific competition pressures Q1 and Q2 acting across the ecosystem. After we compute all values, this is what we get for equilibrium point and the eigenvalues for case study 1 and case study 2. Consequently, for both case study, A3 is an unstable saddle point. This mathematically demonstrates that a completely disease-free coexistent state cannot survive a viral introduction, which is the virus is fundamentally primed to invade the population and become chronic. Since the disease successfully invades the DFE, our system moves to our final steady state, the endemic coexistent equilibrium E4, where the susceptible host, effect host, and non-host population all live together permanently. The complex coordinates for E4 are shown on the slide, representing the ultimate balance of births, natural deaths, disease mortality, and transmissions. By substituting these equilibrium densities back into a final master Jacobian matrix, we can evaluate the long-term permanent stability of our full three-species system. After we compute all values, this is what we get for equilibrium point and the eigenvalues for case study 1 and case study 2. Our interpretation of stability is clear. Since all eigenvalues have negative real parts in both case studies, the endemic equilibrium is locally stable. The imaginary part suggests that the population will go through some temporary escalations after a disturbance, but they will always return safely to this ongoing endemic state. That's all from me. I will pass to Shamimi.
On this slide, we can see the phase portrait for the trivial equilibrium where all populations are equal to 0. The trajectories move away from the origin, showing that this equilibrium is unstable. This means that complete extinction cannot be maintained in the long term. If even a small number of susceptible mice, infected mice, or non-host species are introduced, their population will start to grow. Biologically, this suggests that the ecosystem has the ability to recover naturally and avoid permanent extinction. Here we have the phase portrait for the boundary equilibrium where the non-host species is extinct. The graph shows saddle point behavior, meaning some trajectory approach the equilibrium where others move away from it. Therefore, this equilibrium is unstable. Biologically, only susceptible mice remain in the ecosystem, while infected mice and non-host species disappear. However, this condition is not permanent because a small introduction of infected mice or non-host species can change the ecosystem dynamics. This slide shows the phase portrait when only the non-host species survive. The equilibrium is also unstable because there is one positive eigenvalue. Some trajectory move toward the equilibrium, but others move away from it. Biologically, the ecosystem cannot remain in the state where only non-host species exist. If a few new mice are introduced, they can reproduce and establish the host population, changing the balance of the system. The phase portrait represents the disease-free coexistence equilibrium. Here, susceptible deer mice and non-host species coexist without an infection. The trajectory initially moved toward the equilibrium but later diverged because of one positive eigenvalue. This indicates an unstable center point. Biologically, the ecosystem appears healthy and disease-free but is vulnerable. Even a small introduction of infected deer mice can trigger disease transmission and move the system away from this disease-free state. On this slide, we observe the endemic equilibrium. The trajectory spiral inward toward the equilibrium point, which indicates a stable spiral. All eigenvalues have negative real part, so the system eventually returns to equilibrium after small disturbances. Biologically, susceptible mice, infected mice, and non-host species all coexist. The virus remains present in the population, but the ecosystem reaches a stable balance where no species become extinct. So now let's move on to time series part. This time series graph shows the behavior of the population at the trivial equilibrium. All three populations, susceptible deer mice, infected deer mice, and non-host species, decrease towards 0 over time. This represents total extinction. However, because the equilibrium is unstable, complete extinction is unlikely to persist. If a few individuals enter the ecosystem again, they can reproduce and allow the ecosystem to recover. Then, this graph shows that the susceptible deer mouse population approaches a positive stable value, while infected mice and non-host species gradually decline to 0. Eventually, only healthy deer mice remain. Biologically, this means the disease cannot survive in the ecosystem, and the non-host species disappears. The deer mouse population continues to exist in the stable condition without infection. In this time series, both susceptible and infected deer mice decrease to 0, while the non-host species grows and stabilizes at the positive level. Eventually, only the non-host species survives. This means that host species is completely removed, causing the virus to disappear as well. However, this state is unstable because if deer mice return, they can reproduce and rebuild their population. This graph shows susceptible deer mice and non-host species reaching stable positive level, where infected deer mice decline to zero. The ecosystem becomes disease-free. This means healthy deer mice and non-host species coexist successfully. However, this equilibrium is not stable against disease invasion. If even one infected deer mice enter the population, the virus can spread and push the system toward an endemic state. This final time series shows all the three populations fluctuating at the beginning before stabilizing at positive values. Susceptible deer mice, infected deer mice, and non-host species coexist in the long term. Although there may be short-term fluctuation, the ecosystem eventually reaches a stable balance where all populations survive.
So now we will be looking at the bifurcation diagram. So the bifurcation diagram of model 3 with respect to K1 looks like this, where the disease-free unstable bifurcation is constant at 0, while the endemic stable, it has a bifurcation point at around 19 or 18 at K1 equals to 18. Now let's talk about the numerical method to obtain this bifurcation diagram. So the bifurcation diagram was obtained using MATLAB, and one parameter was varied while the others were kept constant. In the case of the earlier bifurcation diagram, K1 was varied because it affects the deer mouse population size and the persistence of the virus. And for all K1, the statistics were calculated by letting the following system of the differential equations to be 0, namely dmz over dt equals to 0. And then we have the other parameters, which is mi and also z. The differentiation of those respect to time is set to 0. Now, these variables which were set to 0 with respect to time represents a susceptible deer mouse population, the infected deer mouse population, the non-host respectively. So the equilibrium, after the points were obtained, the equilibrium mi star was plotted against the K1, the bifurcation parameter, to obtain the bifurcation diagram. The disease-free branch is represented by when mi star is equal to 0, while the endemic branch is represented by mi star when it's positive, which is represented by the red line in the bifurcation diagram. So each of the equilibrium points, the stability was determined by using the Jacobian matrix. So basically, it is just when the eigenvalue is negative, then the equilibrium is stable, while if it's positive, then it's unstable. From the diagram, when K1 is small, the disease cannot sustain itself, which can be interpreted that the deer mouse the population is small, and the disease does not have enough hosts for it to persist. Like it infects, and then the infected dies, and then the disease cannot spread. But if the population K1 is big enough, there are enough hosts so that the disease can spread enough to sustain itself. So the diagram shows a transcritical bifurcation pattern. So now let's look at the analytical method to get the bifurcation. So as you can see, we set the earlier variables to 0, and then solving this will give the equilibrium points of the model. And then there's two types of equilibrium points, which is mi star equals to 0, which is disease-free, or mi star is positive, which is endemic. So to study the equilibria, again, the Jacobian is used to evaluate the equilibrium points and the eigenvalues to determine the stability at each point. The bifurcation occurs if the stability of an equilibrium changes as the parameter changes. So in this case, when the eigenvalue is equal to 0, then bifurcation occurs. At the critical value, disease-free equilibrium loses its stability while the endemic equilibrium becomes stable. This means that the system changes from disease-free to when the Sin Nombre Virus persists.
Next is eco-epidemiological implications of conservation biologies. So first of all is dilution effect at more than 0. So the more evident the dilution species are, the less the prevalent SNVs will be in deer mouse population. So according to this model, dilution agents are species that can help reduce the virus. Hence, more dilution species present, deer mice have fewer opportunities to spread SNV to one another. So therefore, the number of infected deer mice decreases. Next is amplification effect at is less than 0. So biodiversity may inhibit the spread of disease. As known, all organisms cannot be carriers for SNV. So therefore, disease transmission can naturally reduce by higher biodiversity. So the last one for this is conservation significance. So decrease in dilution effect, species can enhance SNV persistence. So the virus can spread much more easily when dilution species disappear. So therefore, this can allow SNV to remain in the population for the longer period. Next, let's dive into the wildlife managers. So first of all is disease surveillance, so monitoring their mouse population density. So managers perform regular mouse capture to calculate the total population density, which is M equal to MS plus MI. And next is habitat management, so ensure balanced wildlife communities. So biodiversity serves as an stabilizing force. Wildlife managers need to ensure that there is no monopolization within the system. Next is management significance, so early intervention can prevent large outbreaks. So waiting until an outbreak occurs is expensive and dangerous. So managers will be able to take preemptive action when the population of mice become extensive. Next is policy markers. So first of all is biodiversity conservation policy. So protect habitats with high species density. By proper protection of this rich ecosystem, policy markers can guarantee that the density of the external agent density A remains high. And then public health protection. Lower infection in wildlife reduce risk of a human exposure. So according to the model, the smaller the number of infected mice, the less amount of virus shed into the environment. So the lower the chance of contracting the disease. Next is policy significance, so integration of environment and public health. Also, according to this model, decision made by the Forestry and Wildlife Department determine of the safety of human living areas. Conclusion, analysis was conducted using an eco-epidemiological model, which is model 3, tracking with the horizontal transmission dynamics of SNV within a population of dice mice, together with another iterating agent. So mathematical and numerical analysis revealed that the effect of external force as a predator was to squeeze the transmission rate of the virus, leading to fewer infection of the dill mouse. So the result that the model move towards an infected-free equilibrium point. So according to the model function as an infected early warning system. So the proof shows that the monitoring the density of wild horse and managing the carrying capacity allows field intervention to be implemented before a virus outbreak. So that's all from us. Thank you.